Okay, thank you very much. Hope you had a good lunch break. Welcome to the session. Let's get started with in-memory processing. We start with the lightning talk by Onur Mutlu. Onur doesn't need a lot of introduction, but he's a full professor at ETH Zurich. And yeah, thank you very much.
Cool. Nope. Okay, I'm being timed, so now I have to imitate high bandwidth memory and actually see if we can deliver high bandwidth. Okay, well, thanks for coming here. I'm going to be very only motivational and just give you examples. Everybody knows all of the things that I'm going to say, I think, but I'm going to say it because it needs to be said multiple times so that we realize what we're doing here, in my opinion. So today, computing is bottlenecked by data. And you know, many workloads are bottlenecked by data. They require rapid and efficient processing of data. And on top of this, data is increasing. And you can see this in neural networks. Both compute and memory requirements are increasing exponentially. It's a beautiful talk by Sean Lee from Cerebras. If you haven't watched it, I'd recommend watching it. But it's not just neural networks. There are a lot of other interesting applications that we've been dealing with, that we're going to deal with, that are coming up. And they're bottlenecked by data, as you can see. And on the mobile end, again, we're overwhelmed by data. Performance and energy is really constrained by the data. I'll talk very briefly about genomics. We had a special session on genomics 2 days ago. I think genomics is an area where data is really exploding because sequencing technologies are so good that they're producing data much more cheaply than we can actually put transistors on a chip. And clearly, our scientific discoveries and medical advancements are bottlenecked by how fast we can process this data. And this is a data generator over here that's great at generating data, but it's terrible at processing data. So I think this picture, if you don't remember anything out of this lightning talk, this picture is probably the best one I would offer you. Essentially, in many domains today, we have specialized machines that can generate data. In genomics, this is one example machine. You saw another example in the previous slide. And then we're moving this data all over the place, even locally as well as globally, to some other machines that are extremely slow. These are general purpose machines. So we have a mismatch here. We can generate data much fast in a specialized way. We move the data far away, and we have slow and inefficient processing capability. So we're wasting a lot of energy and processing power because of the way we set up our system. And if you don't like genomics, videos are another example. Web is another example. You could basically keep adding other data generators over here. And if you missed our session, don't worry. We actually have the papers of our session online as well. Okay, so I think, let me take a step back. Basically, data is overwhelming our machines today. It's overwhelming the storage and memory capability, communication capability, and computation capability. And if you look at the fundamentals of computing, you need to have both the three of these things. Today, we've actually decoupled these three things from each other. As a result, I think we have this problem of data movement all over the place. Essentially, we not only decoupled them, but we actually made computing, let's say, the king, if you will. That's the most important part of the processing system. And everything has to go to the computing unit so that I can actually process it. That computing unit can be a CPU, GPU, FPGA, your favorite accelerator. Doesn't matter. Data has to get delivered there so that you can process it. No other parts can process the data. So this comes at a great system cost. Now I'm going to put some numbers in that system cost, but basically we're wasting a lot of energy because of this. And we're wasting a lot of performance as well because all of these resources are getting wasted. This is going very slow. So if you look at a general purpose computing system, it looks like this today. Basically, most of the resource of a system is dedicated to storing and moving data. Yet our system is still bottlenecked by memory. And if you don't like my picture, this is a picture from AMD. That green box is really the caches. And we're putting more caches. Then the question is this the right thing to do? And then it doesn't like, if you don't like AMD, there's IBM. And then this is my favorite, Apple. Basically, you have a computing chip that's essentially a lot of SRAM. Everything else is DRAM, storage, etc., but they cannot do operations on the data. Okay, so what's the cost of this? So we analyzed this in multiple papers. This is the work with Google. We found out that more than 60% of the total system energy is spent on data movement in a mobile system, ignoring storage. Once you go to storage, this becomes even worse, actually. And in large machine learning models that are used at Google, you get more than 90% of the total system energy spent on memory. So are we doing the right thing? And this is happening because data movement is actually much more costly than computation today. A sophisticated arithmetic operation is very cheap in terms of energy, whereas a DRAM access is 2 to 3 orders of magnitude worse in terms of energy. And if you actually want to look at a simpler arithmetic operation, which everybody wants to do in machine learning, for example, today, the disparity between the energy of that simple operation and memory access is more than 3 orders of magnitude, as you can see. And okay, that was the energy cost. There's a performance cost also. This is data from Google. According to Google, this is all of their data center workloads. And you can see that most of the time, the processor is waiting for data to come back. So essentially, We're wasting energy, but we're not getting the performance also. These processors are not utilized. Most of the time, they're waiting for data. Okay, so the problem is, I think, and this is why we're here, the processing is performed far away from the data, and we do not want to move data. We're in a regime where we need a paradigm shift to enable computation with minimal data movement. We want to compute where it makes sense, where data resides. Today, we have no option. We would like to enable options everywhere in the system, and we want to make computing architectures more data-centric. So I call this processing data where it makes sense. If you look at a system like this, all of these dark components over here should probably be able to do computation, including the sensors. Today, we have no choice, as I said. So I will go through the slide relatively quickly, but we are going to use memory as an accelerator in many of the talks that we see today. In the future, I believe there's a model where all of the agents are distributed and they're all equals in terms of computation capability. But I'm not even talking about that. I'm going to use memory as an accelerator. And even then, there are many questions over here. How do you design the memory, processors, software and hardware interfaces, system software compilers and languages, and algorithms and theoretical foundations so that we can actually make sense out of it and take advantage of it? Clearly, this is an across the stack problem, and there are many questions which I'm not going to answer, but there will be some papers that talk about some of these issues today. So as I said, the mindset is memory as an accelerator. Why don't we have actually some capability on the memory side to do processing? Because we're putting a lot of capability on the other side of the memory bus. And this is an old idea. I should also acknowledge that this idea was developed in the 1960s. This is the earliest paper I could find about this. If you actually find other papers, please let me know. And this is a concurrent paper by Harold Stone that argues for the same thing. So why is it interesting today? I think it's important to revisit some of these ideas. And today we're revisiting the ideas because we're having huge problems with memory technology. Memory technology scaling is not going well, and we need some intelligence on the memory side to overcome some of those scaling issues. I will not have time to talk about this, but this is fascinating, I think. And we're also having huge demand from applications and systems. As I said, data access is a huge bottleneck. We're limited by energy and power, and data moment energy is dominating computation energy. And today we want performance, energy, and sustainability all at the same time. So everything is really pointing to minimizing data moment. So we're squeezed in the middle. So again, we don't have time, so I'm not going to talk about the technology scaling aspect, but if you actually have computation in your memory control, you can do much better memory technology scaling. And the systems and applications are pulling us to actually do something different in memory. And the good news is today, things are moving. You may know about the hybrid memory cube, and you may know about automata processing, but more recently, there are companies that are putting processing power inside the DRAM chips. This is UpMem. They have processors inside, next to each bank inside the DRAM chip. This is Samsung. They have accelerators for machine learning. SK Hynix and Samsung and Meta have this memory module. And Alibaba is also designing their own DRAM chips to do this recommendation inference. So the good news is there's momentum in the industry because of these reasons, in our opinion. Okay, so if you're interested, there's a lot more information out there. We've been writing some papers about it. I would recommend people to take a look at it. We keep updating this primer. And we also have a processing in memory course. If people are interested, you can attend it live stream. And we've been organizing real processing in memory tutorials at major architecture conferences. Maybe DAC is a good place to organize these. And you can find a lot of information online. Now, let me actually spend the last 2 minutes covering some examples very quickly. I think there are two ways of doing processing in memory, fundamental ways. One is using and the other is near. Actually, I would like to extend this taxonomy a little bit because there's a lot of confusion in the naming of processing in memory, in my opinion. In my opinion, there are three things that distinguish a processing in memory technology. One is the nature of computation, the other is the technology you use, and the other is the location of computation. And these are three distinct things. Nature is using means that you use the operational principles of properties of memory structures to actually do computation. You don't add logic. Whereas near means you add logic close to the memory structures, just like we're doing today, right? So these are two fundamentally different nature. And then you can do the processing in different technologies. You can see that there are many technologies that are discussed in DAC. And then you can put them in different locations in the system. So if I have to categorize a PIM system, a tuple of these three determines the PIM type. And then you can combine multiple PIM types in a system, right? Actually, if you think about this taxonomy, a CPU is part of the PIM system, and it can be categorized that way. Okay, so an example PIM type, I'll give you one example from DRAM, and then I will conclude. Basically, we're going to look at the nature using DRAM, and the technology is DRAM and locations main memory. So we're going to look at processing using DRAM in main memory, and I think there will be some papers related to that today. So basically, if you look at DRAM, clearly it's one of the major technologies that we have today. You can do bulk operations in DRAM. You can do bulk bitwise and or not majority, copy, initialization, zeroing, and also random number generation. And then who knows what else? I should actually put question marks over here because that's the future, potentially, of research. So you can do this at low cost using the analog computation capability. For example, activating multiple rows can perform computation. And you get significant performance energy improvements if you do that. I'm going to give you one example very quickly. These are 3 DRAM rows, 3 DRAM cells. If you concurrently activate these 3 rows, what you get is a majority function, bitwise majority function of those 3 rows. So it's a block bitwise majority operation, which is great, which could be expressed as block bitwise AND or block bitwise OR. And then you just need an inverter on top of this so that the system can become functionally complete. Again, I don't have time to go to details, but that inversion actually is achieved already here. Oh, sorry. Something is happening with my, yeah. Okay, so you can accelerate some applications using this, block bitwise operations, and you can actually get significant performance energy improvements, as you can see. Now, I will not bore you with other things, but we need to make this programmable. That's going to be important. And we can actually do other things like lookup table-based execution, true random number generation. So we want to actually do other things in memory, in flash, and in other technologies. I just give you one example. So to this end, we actually been developing real processing using memory prototypes. You can actually download the source code. We'd be happy to support it. It's able to do in DRAM copy and initialization as well as true random number generation. At a system level, you can actually study these techniques. And with that, I think I will end, but I will mention one thing that's really important. With all of these technologies, we need to adopt them. So adoption is a huge challenge. And there are a lot of things to consider in terms of adoption. Again, I don't have time to go over all of these, but you can see that we need to really look at the entire stack to enable adoption. There's one talk over here in this particular session that talks about address translation, for example. That's going to be important, but there's a lot more over here, as you can see. So we should not be ignoring these adoption challenges. It's not just about the technology, hardware technology. It's really about how to get it adopted in the entire system. Okay, for that, we need to revisit the entire stack. So with this, I will conclude. I'm happy to take any questions if you have time. I'll leave it to the session chair, but I'll be around.